Yeah, thank you. I'd like to begin by thanking to the organizers, especially Daniele and Gerald, for giving me this opportunity to at this wonderful workshops in this beautiful city. And today I'm going to talk about the classifications of rational conformal field theory in two dimensions in relation to the classification of the topological phases of matter in three dimensions. So this talk is based on my previous works in collaboration with Jinbom Bae, Kim Young Lee, Lingfeng Lee, and Jihao Duan. So at that time, Jinbom was at Oxford, but unfortunately he moved to finance. Maybe fortunately. And Kim Young, as some of you know very well, he will retire soon. And Jihao is now at Queen Mary London. So let me start. So as some of you know very well, there has been a lot of activity to understand the physics of topological phases of matter, both in condensed matter physics and high energy physics. One of the main questions in this field is to understand is how to characterize these topological phases of matter. Oh wait, which one? This one, matters. And actually, there are two different approaches to attack this problem. And let me first start with the first approach, which is the bulk approach. So for that, let me consider some system which is in the topological phase. So topological phase is basically a gapped phase. So in the infrared limit, we are left with nothing except the vacuum. Some of you may wonder why we have to study this boring theory. The reason is this vacuum is not completely trivial, as I will show you later soon. And since it is not completely trivial, the low energy physics of this topological phase can be described by the topological field theories. So one of the prominent examples is the Chern-Simons-Gay theory in three dimensions, which describe the low energy physics of fractional quantum Hall systems. And as I told you, the system in the topological phase is basically gapped, so everything becomes massive. So in the infrared, we just have so-called quasi-particles. No, this one, quasi-particles, sorry. Oh, sorry. Okay. Quasi-particles, in other words, the external particles. So in the language of topological field theories, these quasi-particles can be identified as a loop operator of the topological field theories. For instance, in the case of the Chern-Simons-Gay theory in three dimensions, this quasi-particle can be identified as a Wilson loop operator. So in three dimensions, those quasi-particles are known as the anyons. And the systems of anyons have very interesting mathematical structure, such as the Braden group, fusion algebra, F matrix, R matrix, and so on and so forth. And those structures are subject to various consistency conditions. And the system of this anion, together with these consistency conditions, can be nicely summarized by the so-called modular tensor categories in the modern language of mathematics. Oh, not this one. Therefore, it is quite natural to propose that one can characterize, so the modular tensor category, this is for the bosonic topological phase. So it's natural to propose that we can characterize the bosonic topological phases of matters in three dimensions by searching for the systems of anyons, which has a consistent modular tensor categories. So this program has been done successfully by a number of mathematicians and the physicists in the condensed matter physics, such as the Xiaogang Wen and his colleague. More precisely speaking, what they did is to find systems of anyons which has well-defined modular matrices. By well-defined modular matrices, I mean this modular matrix have a well-defined fusion algebras, but they didn't actually check whether the corresponding annual systems also satisfy more complicated and sophisticated consistency conditions, such as the pentagon identity and the hexagonal relations. But still, their results are very, very impressive. And after their success, people would like to classify the fermionic topological phase in the 3 dimensions. So what is this fermionic topological phase? One of the simplest example is the U1 Chern-Simons gauge theory, where the Chern-Simons level is given by the odd integer rather than even integers. So in this case, the vacuum expectation value of the Wilson loop actually depends on the choice of the spin structure of the given 3-dimensional manifold. Since some observable depends on the choice of the spin structures, we can call this theory as a fermionic series. But and for that purpose, for this purpose, one first has to generalize this modular tensor category to take into account the fermionic nature of the system. The problem is in the market, actually, there exist a couple of different looking generalizations, such as a super modular tensor category, spin modular tensor categories, and fermionic modular tensor categories. And at the time when I just started thinking about this problem, it wasn't clear, at least to me, which one of these generalizations will give the correct classifications of these fermionic topological phases of matters in 3 dimensions. For now, I barely understand the relation between these two, but still it's not clear. So in order to circumvent this difficulty or subtlety, and in order to go beyond having just modular matrices with well-defined fusion algebra, I'd like to take the second approach, which is the boundary approach. So for this, I'd like to place the system in the topological phase in the 3-dimensional space-time, which has a 2-dimensional boundary. So in this case, one can argue that there exists the massless excitation on these 2-dimensional boundaries, which are also known as the H mode on the boundaries. And the existence of this massless excitation on the boundary can explain why the vacuum of this topological phase is not completely trivial. And furthermore, one can argue that the physics of this H mode on the boundaries can be controlled by the chiral part of this 2-dimensional rational conformal field theories. In fact, there is very interesting relation, one-to-one correspondence between the bulk physics and the boundary physics, such as each anion in this bulk will correspond to each chiral primary of this rational conformal field theories. And the statistical spin of this anion will correspond to the conformal weight of the corresponding primary. And furthermore, the expectation value of the loop operator for this anion spectrum of this topological field theory defined on solid torus will compute the conformal character of this chiral primary on torus. And for instance, F matrix and R matrix we can compute from this conformal field theories will be identified as the F and R matrix of these anionic systems, and so on and so forth. So based on this bulk boundary correspondence, one can expect that having consistent 2-dimensional rational conformal field theories will imply the existence of the well-defined anionic systems compatible with these modular tensor categories in the case of the bosonic topological phase. So in other words, this F matrix and R matrix you can compute from the CFT. They are guaranteed to satisfy the pentagon identity and the hexagonal identity whenever the CFT is well defined. Mm-hmm. For the purpose of classification of the modular tensor category, maybe we need this modular tensor category. But what people did is they just found the modular matrix only. They didn't check whether F metric. They didn't know how to compute the F matrix and R matrix compatible with this pentagon identity. Not even characters. Yeah, just S and T matrix. Yeah, and from using this modular matrix, you can compute the fusion algebra based on this Berlin formula. Yeah, and just that. Yeah, they just stopped there, but still quite impressive. Okay. So then, what about the fermionic topological phase? We just need to search for the consistent fermionic rational conformal field theories. There is no other options. This is the only thing we need to do. So, and this is the goal of the today's talk. Any questions so far? Mm-hmm. Oh, that's right. So it's a, in a sense, it's a finer classifications because two different conformal field theory may correspond to the same modular tensor categories. All right, so let me first remind you what these fermionic rational conformal field theories are. So as all of you know very well, in order to define the theory of fermions on two-dimensional space, we first need to specify the boundary conditions along every cycles of this two-dimensional manifold, which is also known as the choice of the spin structure of the given manifold. So for instance, on two torus, we have four different boundary conditions, such as which is described in this cartoon. This rectangular is for the torus, horizontal line is for the spatial circle, and vertical line is for the temporal circle. Then you can impose Liouville-Shor boundary conditions. Here, where the Liouville-Shor boundary condition refers to the anti-periodic boundary condition for fermions. Or you can impose the periodic boundary condition along the temporal circles and Liouville-Shor boundary condition along this circle, where this Ramon boundary condition refers to the periodic boundary conditions, or NSR and RNR. So we have four different boundary conditions on two torus. And for simplicity today, I'm gonna use the shorthand notation for these four different spin structures, NS, NS tilde, R, and R tilde. Well, everybody knows that the torus is invariant under the modular transformation group, so such as SL2G. But now, this torus is endowed with the boundary conditions. And it is fairly clear that the full SL2G transformation will not preserve these boundary conditions. So for instance, the torus with NS boundary conditions, this is invariant under the S transformations, which is one of the generators of SL2G. But on the T transformations, this boundary condition will be mapped to different boundary condition, NS tilde. So this is another generator of SL2G. Only when you perform this T transformation twice, then this NS boundary condition will be invariant. So the torus with this NS boundary condition will be invariant under the transformation group generated by S and T square, which is nothing but the gamma theta 2. Similarly, you can argue that NS tilde boundary condition will be invariant under this group, gamma upper 02, and R boundary condition will be invariant under the gamma lower 02. And in fact, these are nothing but the level 2 congruent subgroup of the SL2Z. And therefore, we can expect that the torus partition function of the torus partition functions of the fermionic series with this boundary condition will be invariant under the corresponding modular symmetry group. You know, for NS boundary conditions, gamma theta 2, NS tilde, invariant under the gamma upper 02 and gamma lower 02. In Hamiltonian interpretations, the torus partition function with this boundary condition can be written as follows. The trace is now performed over Hilbert space in the Liouville-Shor sector, weighted by Q to the L0 minus C over 24, Q bar to the L0 bar minus C over 24, where Q is given by exponential of 2 pi I tau, where tau is the complex modulus of the torus. And L0, L0 bar are nothing but the Virasoro generators in left-moving sectors and right-moving sectors, whose eigenvalue can be determined by the conformal dimension and spin. and C is the central charge of the given theories. On the other hand, for this ns tilde boundary conditions, the torus partition function can be written as these expressions. Again, trace is performed over Hilbert space in the Liouville-Shor sectors because we impose the anti-periodic boundary conditions along the horizon, special circles. But now, because we impose the periodic boundary condition along the temporal circle, we need to insert this operator minus 2df. Finally, for this torus partition functions with this R boundary conditions, the corresponding partition function can be written in this way. Now trace is performed over Hilbert space in the Raman sector. And for the rational conformal field theories, this torus partition function, each torus partition function can be written as a finite sum over holomorphic functions of tau times anti-holomorphic functions of tau. So this is the definitions of the rational conformal field theories, meaning that this rational conformal field theory has finite numbers of chiral primary. This is the definitions. So here the primary means primary with respect to a certain extended chiral algebra, which includes the Virasoro algebra. And here this conformal, this holomorphic function of tau can be identified as a conformal character of this primary, chiral primary of this two-dimensional conformal field theories. And the number of this finite number of this conformal primary, the chiral primary, is the same as the number of this edge mode on the boundary, which is the same as the number of the anion in the bulk topological phase. And since we would like to make this partition function invariant on the, for instance, in this case, gamma theta 2 transformations, we can show that this conformal character must transform as a vector valued modular form with respect to the corresponding modular symmetry group, in this case, gamma theta 2. More precisely, this conformal characters for this NS boundary condition should satisfy those transformation rules. The first line is for the T-square transformations, and the second line is for S transformations. And T-square S are generator of this group gamma theta 2. So in other words, this gamma theta 2 transformations are realized linearly in this D-dimensional space, vector space. And otherwise, we cannot make this partition function invariant on the gamma theta 2 transformations. Similarly, we can argue that using the same argument, this conformal character for NS boundary tilde boundary condition and R boundary condition must transform as a vector value modular form with respect to corresponding modular symmetry group, gamma upper 02 or gamma lower 02. And in the limit where tau goes to I infinities, meaning low temperature limit, we can expand this conformal character in powers of Q. For instance, this conformal character for NS boundary conditions can be expanded in this way. And there we can read off the conformal weight of the primary in the NS sector and the central charge from the exponent of the leading term in this Q expansions. On the other hand, this conformal character for NS tilde boundary condition can be expanded in this way. And you can see that the signs for half integer spin mode are all flipped. This is because we insert -1 to the F operator inside the trace. Therefore, the fermionic state will get additional minus sign. And and finally, this conformal character for R boundary conditions, we can also read of this conformal weight of primary state in Raman sector from this exponent alpha IR, the leading term in this Q expansions. And we can show that for rational conformal field theories, those exponent alpha INS and alpha IR, or equivalently central charge and the conformal weight, they are all rational valued. And that explains why this conformal field theory is named as the rational conformal field theories. And finally, let me discuss a few more properties that this conformal character of conformal field theory should have. The first one is integralities, and the second one is the positivity. Meaning that whole coefficient in this Q expansion of conformal character must be integer valued. And in particular, this AN here and BN here, which appears in these two expansions, they must be non-negative. This is because this coefficient will count the number of the operators carrying the specific conformal dimension and spin. So if one of these conditions is violated, we lose the notions of operator countings. So in that case, we cannot regard this vector value modular form as a conformal character of well-defined conformal field theories. So this is the consistency. This is the conditions that conformal character should satisfy. And another condition is the weak holomorphicity, saying that these conformal characters are holomorphic functions inside the fundamental domain. And the final condition is the presence of the unique vacuum. So in this NS sector, we have a conformal character corresponding to the vacuum state, and it should expand it in this way, meaning that the first coefficient must be 1. This is because the corresponding state will this state will correspond to the identity operator of the CFT via the operator state correspondence. So if this number is not 1, then it shouldn't be the conformal character of the conformal field theories. And if you want to consider some unitary conformal field theories, we can also impose these unitarity conditions. Right. So, given these backgrounds, we can study the space of the Fermionic rational conformal field theories by studying the space of the vector value modular form with respect to the gamma theta 2 or gamma 02, subject to various physical constraints such as integrality, positivity, weak holomorphicity, and the presence of the unique vacuum, sometimes the unitarities. And the conventional way to study or at the same time systematic and practical approach to study the space of the vector valued modular form is to use the so-called modular linear differential equations. So modular linear differential equations is a linear differential equation which is invariant under the modular symmetry transformations. So let me first consider this NS boundary conditions. And this is the most general form of this modular linear differential equations, where d tau is a kind of covariant derivative with respect to tau, where the second Eisenstein series, this is holomorphic, not the non-holomorphic. So the holomorphic Eisenstein series play a role as the connection, and m is the weight of the modular form on which this derivative is acting on. And this derivative is called the Serre derivative in the literatures. And here phi sub k, meromorphic modular form, any meromorphic modular form of weight 2 times d minus k with respect to gamma theta 2, then you can show that this differential equation will be invariant under these transformations. Meaning that d independent solutions to these equations will transform to themselves under gamma theta 2 transformations because this differential equation is invariant. In other words, the solution to these differential equations have to transform as a vector value modular form with respect to gamma theta 2. So we would like to regard these solutions as a conformal character, candidate conformal character of putative conformal field theories, but it is not guaranteed at all whether this solution will satisfy the physical constraints such as the positivity, integrality, and weak holomorphicity, and so on and so forth. In fact, using this physical constraint, you can restrict the possible form of this, for instance, this function phi sub k. For instance, let's consider some weak holomorphicities. Let's explain how this weak holomorphicity can constrain the possible form of this the coefficient function phi sub k. So for that, let me assume that we have conformal character of well-defined conformal field theories. So it is guaranteed that they already satisfy the physical constraint. And then you can show that this conformal character are the solution to differential equations, where this phi sub k can be written as a ratio of the Ranskian functions of chi, where the Ranskian function wk is given by this expression. This is just a ODE 101. If you know the solution, then you can reconstruct the differential equation. And since chi sub I, as I told you, they are weakly holomorphic modular, weakly holomorphic, and therefore this Ranskian wk also becomes weakly holomorphic. Therefore, these coefficient functions that appears in this modular linear differentiation are allowed to have poles only at the zeros of this Ranskian function wd. And it's quite convenient to classify this modular linear differential equations by the order of poles of this coefficient function phi sub k, labeled by L over 2. And when this value becomes 0, you can show that the space of this function phi sub k is finite dimensional. More precisely, they can be generated by a certain combinations of Jacobi zeta function in this way. And when L equal to 1, this space is again finite dimensional. And in this case, this function can have poles only at the very special values of tau, which is tau equal to I, the orbifold point, and so on and so forth. So you can determine, because this space is finite dimensional, you can determine them using the finite numbers of physical data. And once you fix the modular linear differential equations using the physical data, you can solve the differential equations, get the solution, and see whether the solution will satisfy the physical constraint. So to illustrate this idea, let me work out some simplistic example, d equal to 2, meaning that we are looking for CFT having two conformal characters, and L is less than or equal to 1. In this case, we have the most general differential equations, modular linear differential equation for NS boundary condition, can be written as these expressions, where this coefficient function phi 0 and phi 1 can be written as follows. And as you can see, there are 4 unknown parameters, mu1, mu2, mu3, mu4. And you can determine them by the value of the central charge and the conformal weight in the NS sectors and R sectors. It's quite interesting because we are looking for the modular linear differential equation for NS boundary condition, meaning it's NS sector differential equations. But in order to determine this modular linear differential equation, you need some data from the different sector, Raman sector. So using this physical data, once you fix this modular linear differential equation for one boundary conditions, then using T and S transformation rule of the Jacobi theta functions, you can also determine the differential equation you need to solve for different boundary conditions, NS tilde and R boundary conditions. So in order to scan or explore the space of this Fermionic rational conformal field theories, what we need to do is to take the following strategies. So pick just random rational numbers for this physical data, alpha I NS and alpha I R, or equivalently the central charge and the conformal weight in NS and R sector, and insert those numbers to fix the modular linear differential equations, solve it using the Frobenius method, and check whether the solutions will satisfy the rest of the physical constraints like integrality, positivity, the presence of the unique vacuum and unitarities. If there is one of these physical constraints is violated, there is no conformal field theory at that values for this exponent. Then you need to change the rational numbers and repeat this procedure again and again and again. Hmm? Oh yeah. And so this procedure is called holomorphic modular bootstrap program. And this sounds quite interesting and exciting, but practically it is impossible numerically simply because we cannot scan all possible rational values of these numbers. This is for physical data, alpha INS and alpha IR. So it's quite disappointing, but it's too early to give up. In fact, one of the physical constraints we haven't used highly constrain the possible values of this physical data alpha INS and alpha IR. So you don't need to scan all rational values. There are very specific values allowed for this alpha INS and alpha IR. And that will improve the efficiency of this holomorphic modular bootstrap to explore the space of the Fermionic rational conformal field theories. So what is the physical condition? It is the integrality condition. So there is a so-called integrality conjecture saying that the vector value modular form with respect to gamma theta 2, which obey the integrality condition, must be the vector value modular form with respect to another group, which is the gamma theta 2 mod gamma n for some even integer n. In fact, this integrality conjecture was proven recently, a couple of years ago, in the case of the bosonic theories. There, this gamma theta 2 is replaced by SL2Z. But this integrality conjecture remains a conjecture for fermionic cases, but I believe that this conjecture is true. Mm. Mm. Gamma n, yeah. It was proven 2 years ago, maybe. I will come to that point later. I don't remember the name, sorry, but I can search the name after talk. Any other question? All right, so what this integrality conjecture says, where was I? There must exist a certain number n, even integer n, so that the vector value modular form on the left-hand side, which satisfies this integrality, must be invariant under the gamma n transformations, where this gamma n is defined as this one. And nice thing about this integrality conjecture is that this group, unlike this group, it is a finite group. And we know everything about the finite group. And that will improve our ability to do this task. So in other words, using this integrality conjecture, one can transform a problem searching for the vector value modular form satisfying the integrality properties to another problem, which is a representation theory problem of this finite group. And as you will see, from this representation theories, you can highly constrain the possible values of this exponent, alpha INS and alpha IR. In other words, central charge and the conformal weight. And that, because of this conventional holomorphic modular bootstrap method is highly improved. Unbounded. Oh yeah, it's a similar. I guess so. Yeah. Mm. Sorry. Uh-huh. It could be anything, but you will see that because of the representation theories, there is some constraint on this end as well. Yeah, you will see this soon. So before we discuss about the consequence of this integrality conjectures, let me make some few comments regarding this finite group. We can actually argue that this gamma theta 2 mod gamma n is you can see this green letter. Two Silo subgroup of this another finite group S2Zn. And this is very nice because mathematicians already classify all irreducible representations of this finite group. And since this finite group of our interest is a Silo subgroup of this one, there exists some algorithm to generate the character table of this finite group using the character table of this one. For instance, there is a computer program called GAP. So using that program, you can immediately generate this character table of this finite group. So keep that in mind. So let me first discuss about the physical meaning of this capital N in even integers. What is that? So to understand this, let's consider these n's copies of T transformations, which become identity in this finite group. So when you perform this T transformation n times on this conformal character for ns boundary conditions, it will satisfy this relation. This is because you can easily understand this from the Q expansion of this conformal character. But what integrality conjecture says, this is identity, so it shouldn't be rotate. This conformal character must be invariant, meaning that we have the second equality here. So from these two, you can see that this exponent alpha I and s must be mi over n modular integers, where mi is any certain number, integer from 0 to n minus 1. So in other words, this n is the least common multiplier of the denominator of this exponent. Yeah, because we are talking about the rational conformal field theories, we have finite numbers of this exponent, so we always have this kind of number. So we can easily see that this conformal character for rational conformal field theories, there must exist some n, so that this t to the n transformation is trivial. But what integrality conjecture says, conformal character is not only invariant under this t to the n, but entire gamma n transformations. Yeah, that's what integrality conjecture implies. Yeah, same thing. You should take a smallest number, the least common multiplier. Yeah. Any other questions? Yeah, it's by definition it's an identity, but yeah, not only this, but entire gamma n transform will be trivial. Yeah, that's what integrality conjecture says, and that's the condition for this coefficient become integer valued. Oh, okay. N over 2? L over 2? This is, now I understand. This, yeah. Not only I, it could be any point on inside the fundamental domain. Yeah, but for this particular value, L equal to 1, is only allowed to have poles this point. Yeah. Gamma 0, 2. Yeah, gamma theta 2. Yeah. Any other questions? Uh-huh. Let's say that again. So, they are allowed to have poles or curves as well. Yeah. You mean the conformal character? Yeah. But they should be holomorphic inside the fundamental domain. And using this, let me go on. And using the representation theory of this finite group, you can show that for each values of D, so D is the number of the anion or number of the primary of this conformal field theory have. Actually, there exist finitely many values of for n, meaning that if you fix the number of anions or primaries, you don't need to scan all possible even integers. There are only finite numbers of n you need to take into account. So I summarized this table in this. I summarized the result in this table for small values of d, and as you can see, there are just finite numbers of possible finitely many possible values for n. Even this is quite nice, but actually we can do much better than this. Using the character table of this finite group, you can actually determine the values of these 2 times alpha ins and alpha ir modular integers. So let me explain how this character table will determine this value. First of all, you should notice that the value of this 2 times alpha ins will determine the eigenvalue of the modular matrix of t-square transformations. This is because, well, in order to understand this, let's consider this t-square transformation, which is an element of this gamma theta 2 mod gamma n. By definition, it must satisfy this relation. This is the definition of modular matrix, by the way. And using the Q expansion of this conformal characters, it also satisfies the second relations. So from these two, you can see that this matrix should be written in this way. Therefore, this value will determine the eigenvalue of this matrix T square. Once you accept this, then you can express character of else copies of T square transformations in terms of these eigenvalues. Because it's just by definitions, character of this T square to the else power of the T square for each L can be written as the trace of else powers of this matrix. So you just insert here and compute it. Then this character must be written in terms of this eigenvalues. But if you know the character table, you can read off this character by immediately. If once you can identify the conjugacy class, which contains this corresponding transformation element. So from these procedures, you can determine the eigenvalues of this matrix. In other words, you can determine this value 2 times alpha I ns. So to illustrate this idea, let me consider the simplistic example, the n equals 4. And let me say we are interested in the two-dimensional representations, meaning that the conformal field theory has two chiral primary. So in this case, this is the character table you can generate using the computer program, gamma theta 2 mod gamma 4. And you can argue that the t-square transformation is contained in this conjugacy class labeled by 2a. And double copies of t-square transformations, which just become identity in this case, should be contained in this conjugacy class 1a, labeled by 1a. And we are interested in this representation, ninth representation, which is a two-dimensional representation. And the characters of our interest, therefore, is given by 2 and 0. And using these two numbers, you can determine the eigenvalues of this matrix T square by plus and minus 1. And from that, you can determine these values of 2 times alpha 0 ns and 2 times alpha 1 ns by 0.5 modular integer. But and you can also, not only this ns sector information, you can also determine the Raman sector, the physical data in the Raman sector as well. Although this character table is for ns sector. To see this, let's consider this transformation, this one, Ts times T times inverse of Ts. You can argue that the eigenvalues of this matrix, the modular matrix for these transformations, can be determined by the values of this alpha 0, alpha 1 r, and alpha d minus 1 to the r. This is because the eigenvalues of this matrix would be the same as the eigenvalues of this matrix and eigenvalues of another matrix, the modular matrix of T transformation in the Raman sector are the same. The reason is any vectors in this boundary for this boundary condition can be mapped to a vector in this NS boundary conditions by using the TS transformations. So once you accept it, you just do the same. You just follow the same steps express the character of this element in terms of this eigenvalues, which are determined by this value alpha 0, alpha IR. And using the character table, just read those characters, and then you can determine the eigenvalues. Then you can determine these values, alpha IR. So let me consider this example again, n equal 4, 2-dimensional representations. Now we are interested in this element, this transformation, which is an element of gamma theta 2. You can argue that this transformation is contained in this conjugacy class, double copies of it is contained in this conjugacy class, and so on and so forth. And because we are interested in this ninth representation, the characters of our interest will be 2, 0, 0, minus 2. And using this data, you can determine the eigenvalues of modular matrix of this transformation by I and minus I, from which you can determine this value alpha 0 R and alpha 1 R, which are given by half and 3/2 modular integer. So as I told you, using the representation theory of this finite group, you can actually determine the values of determine the possible values for this physical data, and I just summarized those results in this table for low values of d equal to 2, 3 character, and 4 character here. Yeah. And what you need to do, just insert this number and fix the modular linear differential equations, solve it, and see whether the solution will satisfy the rest of the physical constraints, such as integrality doesn't guarantee the positivity. So you need to check whether all coefficient is positive. So you need to check whether the solution satisfies positivity condition and unique vacuum conditions and unitarity conditions. It's a fairly straightforward procedures, and computer will do your job for you, but it still takes a long time, even for computers. And this is the result. So this is the classification of the Fermionic rational conformal field theories for low values of D. The rank 2 means 2 character in NS sector, Raman sector, and so on. And 3 character, 4 characters. And these are, and here I only present the conformal field theories, interacting conformal field theory, which doesn't contain any free fermion. Meaning that starting with any this interacting CFT, you just add any arbitrary numbers of free fermion to generate new fermionic rational conformal field theories. And here these numbers, this is numbers for central charge and conformal weight. And actually you can identify known conformal field theories having this central charge, these values for central charge and conformal weight. The numbers in highlighted in this table. But other than that, we couldn't find any known CFT for numbers unhighlighted in these tables. So it seems they are quite new. And also, well, maybe you cannot see, but there are subscript. So here S means the corresponding CFT with those values of central charge and conformal weight. They are supersymmetric. B refers to the case where the corresponding CFT is supersymmetric, but the Raman vacuum will break the supersymmetry spontaneously, meaning that it will satisfy this supersymmetric unitarity condition strictly. It is not saturated. So it breaks the SUGI spontaneously, and N refers to the non-supersymmetric case. And funny thing is this case, the rank 2. So interacting rational fermionic the interacting fermionic rational conformal field theory having 2 characters, it seems that they are all supersymmetric. I don't know why supersymmetric is preferred, right, compared to non-supersymmetric. So we do not understand any reasons, or we do not have any deep understanding why this kind of thing happens for rank 2 case. Sorry? At least you can also argue that whenever these conditions satisfy, the corresponding CFT preserves supersymmetry. Yeah. Of course, for now, we just talk about the spectrum only. But in order to guarantee the existence of conformal field theory, you need to compute the OP. You need to know the information about the OP. But OP, we do that. Yeah, you don't know the OP. Yeah, but still, this is just a candidate. But having consistent spectrum. That. So I think I'm running out of time. So let me stop here and thank you very much for your attention. Do we? This is best. Yeah, yeah. Hmm. Yeah, yeah. No, what I check is that so far we discussed about this NSNS RNS NSR R partition function. If you compute the Ramon partition functions using this data, you can show that it always vanishes or constant, meaning that there is a cancellation between the boson and fermions. We didn't check it carefully, but I guess this decomposition always works. Yeah, it's not a strong constraint. Yeah, right. Mm, exactly. Okay, okay, yeah. As I told you, I didn't check the OP stuff. Yeah, yeah. Mm, exactly. Yeah, yeah, yeah. Right. So what he mentioned is that using this conformal field, performing a rational conformal field theory, you just do the GSO projections to obtain the bosonic conformal rational conformal field theories, and see whether. And as I told you, there is a work classifying the bosonic rational conformal field theories, but this classification program has been done up to 10 anion system, meaning the 10 characters. That means, so if you start from the Fermionic series with rank 2, then corresponding bosonic theory will have at least 6, maximum will be 8. So in this case, you can easily see the corresponding bosonic rational conformal field theory already found by the Xiaogang man. But even here, this 3, if you do the GSO projections, the corresponding bosonic CFT will have at least 9 and maximum 12. So it's already beyond their classification. Yeah. So sometimes have, sometimes no. And this classification is much beyond their classifications. Mm. Oh, so when you increase L, I mean, this is the part I just skipped. So here I just scan the CFT for low values as well, because when you increase L, you need more physical data than central charge and conformal weight. But at the same time, you can generate the rational conformal field theory with higher values of L using these small values of L. So-called, I mean, that procedure is called, you have to use so-called the quasi characters. And using this quasi character, you can easily generate this rational conformal field theories with higher values of L. The question is whether it can all possible rational conformal field theories with higher values of L. But bosonic case, it seems yes. But fermionic case, I don't know the answer yet. Yeah. This is done by Sunil Mukhi mainly. What is the Einstein test? Uh-huh. Sorry. Yeah. uh, it's greater than So you are asking whether C is less than some. Or they are greater than unity. H, the conformal of 8, you mean? Yeah. And many of them sent. Oh, good questions. I guess so. Yeah. Yeah, me neither. Yeah, 17. Yeah. Oh, maybe you can zoom. Yeah, yeah. Yeah. Thanks. Thanks. Yeah, I'm fully relaxed now.